but you can give me that stuff at the end of the class. You know. First, start with lecture materials. Now, to give you intuition for what we're talking about today, well, remember what we were talking about our last class was this introduction to talking about similar concepts, but in the angular way. So, rather than dealing with x's, we are now dealing with thetas. Rather than dealing with velocities, we were dealing with omegas. Rather than accelerations, we were dealing with alpha. Okay? And rather than dealing with mass, we were dealing with moment of inertia. And so over here we had something like kinetic energy was equal to 1/2 mv squared. And I think last time we derived that kinetic energy was equal to 1/2 I omega squared, right?
Yeah. Can you give intuition for moment of inertia again?
Moment of inertia is how hard it is. Well, first off, definition just really quick. The moment of inertia of some object is equal to the sum of all its masses times how far those masses are from the point of rotation squared. So moment of inertia, intuitively what it gives you is how hard it is to rotate an object. The same way that intuitively mass is how hard it is to get an object to move forward or backwards. Moment of inertia is how hard it is to get an object to rotate. The more moment of inertia it has, the harder it is to get it to rotate. If I have grab one of these again. The moment of inertia it takes for me to get this to rotate down this axis is relatively small. It was really easy for me to turn this thing completely around. That took almost nothing. Now if I hold it like this, and I rotate around this axis, now it has much bigger moment of inertia, because it has mass much further away from my axis of rotation. So now, turning that all the way around, I mean even just a half turn, was way more before than rotating this a full 360 degrees. That's almost nothing.
Yeah.
So that's moment of inertia.
Okay.
It depends on both the mass and how far that mass is from your axis of rotation. And the further away it is from the axis of rotation, the harder it is to rotate it.
Yeah.
Make sense? And so I think last time we derived those energy equations. Today what we're going to be focusing on, over here we say the force is equal to mass times acceleration. Force produces an acceleration. Over here we're going to talk about a concept called torque, and we're going to show that torque is equal to moment of inertia times alpha.
Okay.
Yeah, we'll derive all these things. I just want to give you a big picture of all the similarities we'll be seeing.
What's the Greek letter for the Y again?
That's funny. That's a tau.
Yeah.
And it's a T. More people think like you than think like me. It's probably just the way it is. And then the other major concept we'll be talking about is, over here we talked about momentum, and momentum was equal to mass times velocity.
Okay.
And over here, we'll be talking about angular momentum. We use an L for that. And that is going to be, can you already guess what it is?
Moment of inertia times.
Yeah.
Moment of inertia times omega times angular speed. Exactly. And the same way that when you take the derivative of this, you get this. Oh, sorry, backwards. The derivative of this is this, so the derivative of this is this, and other similar relationships. So you might get confused in, all the new symbols and all the new names, but keep track. We're talking about concepts very parallel to what we've already been talking about, just in the angular sense now.
Okay.
And so if you can keep that in mind, I think as we discuss each one of these concepts, it'll become more clear for you. So those are the parallels we'll be seeing. Now let's jump and give actual intuition really quick for torque. Giving intuition for torque. Have you ever had to change a tire before?
Yes.
And was it ever too hard for you to do with just your hand and you couldn't get the bolts to loosen? And so maybe what you did is you went and you stood on the thing instead to apply more force?
Okay.
You ever try something like that? Maybe, let's think of something else.
on it because I was able to do it.
Okay. let's try, have you ever had a really tight bolt, and with the wrench you couldn't get the bolt to loosen? And then what did you do?
I tightened the wrench and then I kicked it or something.
You never extended it? You never stuck a pipe on there? Common trick.
Oh, yeah.
Okay, common trick. You take like a piece of metal pipe or something like that and stick it on the wrench to make it like the wrench has a longer handle. And then it suddenly becomes way easier. Very common thing that happens. So, because the wrench is longer, it was easier for you to loosen that bolt. You might have noticed that before. If you haven't noticed that, then...
Why is that?
We'll get into that for a second, but just trying to give you intuition for the concept. Or think about a door. Where do they put the doorknob? Notice that they put the doorknob as far away from the axis of rotation as they can. Right?
Mm-hmm.
Go and try opening that door, pushing really close to the hinges, and see how hard it is.
Yeah.
And the further away you get from the hinges, the easier it is to open that door. Till by the time you get clear out to the handle, it's almost nothing. And you'll notice if you push in the middle of the door, you're going to have to push roughly twice as hard to get that door to open as pushing at the handle. And the closer you are to the hinges, the harder it is to push. The further away you are from the hinges, the easier it is to push.
Okay.
To get it to start spinning.
To get it to start rotating.
Okay. That makes sense.
That does? You can produce the same rotation with less force just depending on where you push.
Well, I mean, in the real world, it makes sense.
You have intuition for it.
Okay.
Yes. So, good. Appealing to your intuition is the further out you push from the axis of rotation, the more torque you produce, the more rotation you can produce.
And torque is an application of force, right?
Torque is, sure,
Okay.
applying a force can produce a torque. But you can also say applying a torque is applying force. Anyways, so let's imagine for a second that I have some object here. Here's its axis of rotation. Here's our door. And our door has this length right here. And here's where it ends. So this is a position vector to the point where we're pushing on the door.
So the door length is your radius.
So the door's right here. This is to the position we're pushing on the door. Maybe the door goes past it all the way to here. Maybe it went to here. Who knows? But here's the position that we're pushing on the door.
Okay.
You with me?
Yeah.
Okay. What direction should I push that force to maximize my torque? What will make it the easiest to open that door? Is it when I push out like that? Is it if I push the door straight that way? Is it if I push perfectly perpendicular?
Wouldn't it be perfectly perpendicular?
Perfectly perpendicular.
Why not push in? Like
Push.
a little bit.
That way?
Yes, it's rotating like that. You just push it like that.
Here's the hinges. If I push the door into the hinges, does it open? No. It's to optimize it, you push it perfectly perpendicular. Just trying to give you intuition for our definition that we're about to get. It's pushing up like that. That maximizes the torque. When you have a perfect 90-degree angle here. When you're perfectly perpendicular.
Okay.
Right? So now we'll get our definition of torque and make it make sense with this. Definition. Torque equals the cross product of your position vector, where you're applying the force, with your force vector.
Your force vector. Okay.
Yes. Now, the magnitude of torque, going back to our cross product, is F times R times the sine of the angle between them.
Yeah, and we went over that yesterday, so that makes sense.
So we'll just focus for a second on making sure that this equation makes sense with our intuition.
Okay.
We said that we should maximize our torque when that angle, the angle between them, this theta, is 90 degrees. What's sine at 90 degrees?
1.
1.
Yeah.
Now, how much would the door rotate if I pushed it directly into its hinges?
0.
0. So in other words, if I make the angle between them 0, then the magnitude of torque is 0.
Okay.
Furthermore, what happens if I just pulled the door away from the hinges? What happens if I applied the force perfectly that way?
Well, then it won't be rotating.
Then it won't rotate either.
Yeah.
So the torque would be 0. And so plug in 180 degrees and what do you get?
0 as well.
0 as well. Okay, what about if I apply the force downwards rather than upwards? So we do at 270 degrees.
Wouldn't it just be -1?
Then it'd just be -1. So we're applying the torque in the opposite direction. It's rotating the opposite way,
So it's the same amount of torque, just in a different direction.
in the opposite direction. Same magnitude, opposite direction.
Okay.
That appealing to your intuition?
Yeah.
Why this is the equation?
What happens if you do it on a 45-degree angle? Is it just the
It's
sine
just
of
a
it?
smaller number.
It's just going to be a smaller number. It's not going to be all of it, but it's not going to be none of it. Because if I apply the force at a 45-degree angle, here's F, right?
Yeah.
Well, or at any angle, we'll just call this our theta now for a second. Then we still have our component of our force in our y direction.
Okay.
And we still have the component of our force in, let's point it the other way so both our thetas align. So let's say that we're pointing our force this way at some angle, right?
Yeah.
So here's theta. So here's our force. The force that is doing nothing is going to be F cosine of theta. That would be the amount of force pushing directly into the hinges. And the amount going towards rotating it is F times sine of theta. Which is where that comes from, F sine of theta. And it's scaled up by how far out you go, by R.
Yeah.
If you double the distance, you get double the torque.
So torque is in direct correlation with your distance.
It's directly proportional to the distance and the force. More force gives you more torque, and more distance gives you more torque.
But how does that work? So you're saying if you were a mile away from something, and let's say you had a really long pipe connected to something, and if you move it just a little bit, then it moves the thing a lot?
No, you don't.
Then it's real easy to push.
Oh, real easy to push it.
Yes.
Okay. That makes sense.
Okay. So, rough picture of what torque is. Hopefully you've got a bit of intuition here for torque. Right?
Yeah.
So now let's just remind ourselves of some definitions we've already come across, and particularly alpha, angular acceleration. Alpha was, well, we had omega was d theta dt, right?
Yep.
And then alpha is equal to the derivative of omega with respect to t, or in other words, if I substitute in theta for that, it's the second derivative of theta with respect to time, right?
Yeah.
So alpha is the second derivative of theta with respect to time. Huh? Oh. Thank you. So alpha is the second derivative of theta with respect to time. And now let's remind ourselves also from what we did last week. So we had like a table over here of theta, omega, and alpha. And then we said, how do I get an x, a v, and a tangential acceleration in the linear direction, a linear acceleration from these? How do I get from a theta to a displacement?
Don't you just divide by r?
Multiply by r. Theta times r gives me a distance, right?
Yeah.
Omega times r gives me a velocity. Alpha times r gives me a tangential acceleration.
How about the other part of the acceleration?
The centripetal acceleration,
Yeah.
that one is the one that changes direction. Alpha, if you change your angular acceleration, you're changing the speed. It's the acceleration that goes into changing speed is what we mean by the tangential acceleration. Two types of accelerations. One acceleration is just changing direction. One changes speed. When I change my alpha, I don't change how fast. I don't change the turning direction of something. Let's think about a point on a wheel for a second. So here I've got a wheel, and here I've got a point. Well, it does change the other one as well, but it doesn't matter that it does. The point is, here's a point on the wheel, and this wheel is spinning,
Okay.
right?
Yeah.
So as I increase my alpha, we might have to rehash out some of the same conversation we've already had. The wheel goes in 1 second, it spins its distance theta, right? It goes from here to here. If we call this x0 and we call this x1, then our distance, if theta is in r, then this distance right here, delta x, is equal to r times delta theta, our change of theta. If we call this delta theta rather than just theta, or just displacement, right?
Yeah.
but it gives me the linear displacement. And to get now the linear velocity, how do I calculate linear velocity? I do delta x over time.
And then delta over.
So when I do this over delta t, that's the same as doing this over delta t, right?
Okay.
And so now I get that omega is equal to, or velocity, is equal to r times delta theta over delta t. That's what we mean by omega.
And if you do that over delta.
And now if I look at change in velocity over time,
Okay.
then that's the same as looking at a change in omega over time. And that's going to give me my acceleration is equal to r times alpha. That's where it comes from. But it's your linear acceleration,
Which is your tangential?
which we mean by tangential acceleration. It's the change in speed.
Okay.
That was a speed. V there was a speed.
Yeah.
Because when I do this displacement over time, that's giving me a speed.
What's the formula for the centripetal acceleration?
So I was going way, way back. ACP, there's a couple ways you can write it. We write it one way is v squared over r. Another way you can write it is omega squared times r. And then the author had a really ugly way of writing it using periods, which I'll never use.
Okay.
Okay. So, looking back to our tangential acceleration. Our tangential acceleration is alpha times r, right?
Mm-hmm.
Now we know that force times mass equals acceleration in general.
What?
Force is equal to mass times acceleration.
I'm not sure what I just said, that's what I mean.
Okay.
Okay, yeah.
Okay, whatever I said, I meant this equation. As in general, force is equal to mass times acceleration, Newton's third law. And so if I take the tangential acceleration, or the tangential acceleration, multiply the mass, that gives me the r, tangential force.
Tangential force, what
So just
intuitively is that?
Intuitively, so imagine that we've got some rotating object, where we're applying some force onto moving some object.
Okay.
Well, let's go back to our door example. Here's the hinges on the door. Here's our door coming out like that, right?
Mm-hmm.
If I apply a force, and I apply the force like this, so here's F, then the component that's tangent to it, so maybe I'll draw it up like this so that it's actually tangent to it, we'll put F right there. The component that's tangent to it is right here. This is F tangent. And then this right here, we'll just say F, I don't know, in the X direction, sure, something. But this is the component of the force that's tangent to it. Notice that only this component of the force goes towards accelerating that point on the door, speeding it up or slowing it down.
Yeah.
So only this component of the force affects the tangential acceleration of that point on the door.
What about
Okay.
sine? How's that different from sine?
If we name the right theta,
Yeah.
depending on what you call theta. But from what we had written over here, the tangential force and F times sin theta, same thing.
Okay.
Yeah, I should have made that part. So the component of the force that's tangent to the way we're rotating. And you get why it's called a tangent?
Yeah, that makes sense.
Because this, if we carry this out, it's going to make the arc of some circle. And so this is tangent to that circle,
Mm-hmm.
that line. And that's why it's called that. Okay, so our tangential force, this component of the whole force that we apply, is going to be equal to mass times our tangential acceleration. Right?
Yeah, that makes sense.
Which tangential acceleration is just alpha times r.
Okay.
You with me?
Yeah.
Alright, so finally, torque then, the magnitude of our torque vector, we know is r times f sine of theta, or in other words, r times the force that's tangent to it. Right? Looking at that?
Yep.
Yeah.
Okay, so Torque is R times F tangent, which, plug in, we just barely found F tangent is M alpha R. So we have M alpha R, and then this R makes that an R squared.
Yeah, I see it.
And we were talking about at a particular point with a particular mass. So this was assuming we were talking about point mass. So M R squared times alpha. What's M R squared?
Just a moment of inertia.
Moment of inertia, alpha alpha. So the same way that we had F is equal to mass times acceleration, we now have torque is equal to moment of inertia times alpha. So that was a bit to swallow first thing, so let's do 3 examples to help make this make sense, and then we'll come back, and hopefully I can make sense of my examples. I just like scribbled up the bare minimum I thought would give me enough to reconstruct the problem.
Okay.
Okay, so, oh no, I didn't get the radius on there. .8 meters. Okay, so the first problem, we have a scenario kind of like what we already talked about. Here, right here is a bolt, and a plumber puts a wrench on the bolt trying to loosen the bolt, and he puts something on there to extend out his wrench. So he puts a metal pipe over there. So this total distance here now is 0.8 meters. And it's attached to a bolt right here. This is a wrench on a bolt. You with me?
Yeah.
And the bolt makes with the ground, this right here is an angle theta of 19 degrees. I may exaggerate this longer so that we have some room to write. So the plumber, then just stands at the end of the wrench, applying a force downwards of his weight. And that produces a 900 Newton force. Feel like you understand the physical scenario?
Mm-hmm.
And I think our job is just to calculate the torque. I didn't write it there, but I'm pretty sure that's what we're supposed to do. So what is the torque that the plumber applies here? Looks like scribbling the bare minimum didn't do enough. The wrench makes 19. Find the magnitude and direction of the torque he applies. Magnitude and direction. Okay, so we'll find the magnitude and the direction of the torque he applies.
Okay.
So let's calculate the magnitude of the torque really quick.
Well, we just need to find sine of 19.
Let me just put an F here. We'll exaggerate that force a little bit. So here's our F, right?
Mm-hmm.
Here's the component of the force that's perpendicular to this, right? Here's F tangent. And then here's the other force that does nothing. We'll call it the x direction.
Okay.
And so it's this component of the force that we care about, right? Now this angle is also the same as this angle. This angle and this angle are the same, right?
Yeah.
How can I intuitively make that clear to you without doing the proof really quick? So when I draw straight down, or if I make that a right angle, and I draw that out, these triangles are similar. How can I argue that these are similar really quick, even though my picture's lying? Hopefully we're not going down a bad hole and don't mean something I'm not thinking of. We know that's right and that's right. Do we compare it with the big triangle first? Maybe we compare them both with the big triangle. So let's see if I can make that one make sense. This total angle right here is a right angle, right?
Yeah.
And notice on this little triangle right here, it has this right angle. So that right angle, and looking at the whole triangle using all these 3 points, they both have a right angle, right?
Okay.
And notice that they both have this angle. You with
You're
me?
saying the big and the little?
Uh-huh.
Okay.
This little teeny triangle and then the whole triangle both use this angle right here
Yeah.
for one of their angles.
Mm-hmm.
So they have to be similar. If you have 2 angles the same, 2 triangles are similar. Because the sum of their angles is 180. If they have 2 angles the same, the remaining angle also has to be the same. So the remaining angle, this, is the same as the remaining angle, that.
Yeah, that
Okay. So that angle is the same as that angle. So F tangent then is what?
F times sine of 19.
F times sine of 19 degrees. And it's good that you did what you did. It made sure it made sense rather than blindly following the formula, because the formula can mislead you. Because you might choose your angle such that maybe now F tangent came out the cosine of some angle. So don't blindly plug into your formulas. Make sure it makes sense. So I'm glad you stopped and made sure it made sense that that's the same as that angle. And whoa. And now, see, we were already going down a bad track. In our case, now it's F cosine of that angle.
What?
Because you're supposed to use the sine of the angle between them. And since I happen to choose this angle, I didn't use the angle between them. The angle between them is this angle.
Okay.
And so since I changed the way I decided to write this problem, now it comes out that F tangent is actually F cosine of theta, in our case. I could have redrawn this picture. Let's redraw the picture so that you can see how it would have worked the other way. And it's all because I didn't use the angle between the actual two of them. Instead, I used that angle. So here we have this F force once again. And now, if I want to use the angle between them, if I want to use this angle, I need to make my right triangle kind of hard for me to draw that right, but it's going to look something like that. Something. You with me?
Yeah, I see what you do.
So if we made our right triangle like that, here's F. Now this angle over here is F tangent of theta. And now if we use that angle, which instead of being 19 degrees is going to be 71 degrees, now we can use F sine of theta. Because now, in this case, it is a sine, right, of that angle.
Yeah.
Whereas the way we drew it up here, it's F cosine of theta.
So it's all dependent on how you draw it?
Yeah, it's dependent on what you call theta. I mean, our formula doesn't say, hey, our formula presupposes that theta was always the angle between the two. If you want to blindly follow formulas, then you also have to always force yourself to use that angle. Sometimes it's not convenient to use that angle.
Yeah.
It felt a lot more natural to me to use that angle. I don't know if it felt that way to you guys.
No, it felt like that.
And so if you'll understand the concept rather than blindly memorize the formula, then it's really to say F tangent, and that's just F cosine of theta for how we chose to set the problem.
Okay, that makes sense.
And they both come out the same way. F cosine of 19 degrees and sine of 71 degrees are going to be the exact same thing.
Yep.
So you get the same answer no matter what. I personally like this way of thinking about the picture better, so I'm going to stick with that. So we get this is F tangent, whatever that comes out to be, times now our R. And then we can plug that into our calculator. Fortunately, I remember to bring mine. Unfortunately, none of you guys have one. Still. It's okay, we've got a fourth of the year left.
We're 3/4 the way through.
Not really. We're getting 3/4 the way through the material that we're covering. We're covering chapter 10 today in physics. We're only covering 20 chapters in physics.
Oh, I see.
And so we've got, let's see, our force was, do you remember our force? I erased it. 900 newtons. So I got 900 times the cosine of 19 degrees times our radius, which was 0.8, and it comes out to 681. I'm not sure what the significant figures were on this. Looks like just two significant figures. So we end up just 680. So this is 680. And now what's the units that we're going to put on there?
Well, if it's moment of inertia, and that's mass times radius.
That's not how we calculated it. We did a force times a distance.
So it's
What's the units for
So
force?
you can just do Newton meters.
Oh, there we go. Oh. Okay.
Danger. Newton meters we also sometimes call joules when we're talking about energy. This is not an energy. So don't accidentally put joules on there.
Okay.
All right. So Newton meters are what we use when we're talking about torque. We have more example problems. So next example problem. Next example problem, we have some twine or something wound up around a perfectly cylinder spindle, and we're pulling it off, so it's unwinding off of this thing, unrolling off of it.
Okay.
We know that this thing has some radius r. We're pulling off with some force F. We know the mass of this thing is 50 kilograms. Well, we'll plug in numbers for a second in a second. We know the mass, we know the radius, we know the force being applied, and our job is to find alpha. I should note, we also know it's a perfect cylinder, and so we know the moment of inertia of this thing. What's the moment of inertia for a solid cylinder?
It's like 2/5.
Is that 2/5 or is it just 1/2?
Circle like 2/5.
Yeah, circles were weird. I don't think you care.
Cylinder. Let's see, 1/2. That's just what we use in the problem. Let's go back and look at that table. Solid cylinder, moment of inertia 1/2 mr squared. So we know the moment of inertia for this is 1/2 mr squared.
Okay.
So since we know the mass and we know r, then we also know the moment of inertia. Okay, so that's everything we know about this. We're looking for alpha. What is alpha? Alpha is what we're trying to figure out. So we need the equations. We need to set up some set of equations that will give us alpha.
Well, torque is equal to moment of inertia times alpha.
So I know that torque is equal to moment of inertia times alpha. Wonderful. What else do I know? What else is torque equal to?
F times r times sine of theta.
F times r times the sine of the angle between them. But notice that F is perfectly tangential when you're unwinding something from a circle. So this theta is 90 degrees, so sine of theta is just 1, so it's just F times r
Okay.
in this special case. Does that make sense? And so alpha then is going to be F times r divided by 1/2 mr squared, which is going to be, I'll move the 2 upstairs and cancel out one of the r's. So we get 2F over mr, right?
Yeah.
I think I did that right. So let's plug in our numbers. 2 times our force was, we were pulling with 9 newtons, and we're dividing by our mass, which was 50 kilograms, times our radius, which was 6 centimeters.
Yep.
And we get 6.
That's a nice round number.
So 6. So alpha, we get alpha is equal to 6 radians per second squared. Right?
Yeah. That makes sense.
And looks like they found something else here, so let me see if I missed something on that. What is the cable's acceleration too? So that was alpha. So now we also need to find our tangential acceleration of the cable. I guess it's a cable we're unwinding, not thread. So it's a cable we're unwinding. What's the tangential acceleration of the cable we're unwinding now?
Just alpha times radius.
Just alpha times r. Perfect. So you take 6 times, well, we don't need technically for that. 6 times 0.06 gives me what?
Isn't that just 0.1?
What's 6 times 6?
Oh, 36.
36.
So it's 0.3.
So 0.36 meters per second squared. Apparently you guys were both thinking the same way, but it makes no sense to me, whatever you were thinking.
I think we're just thinking pi.
Yeah.
0.36 meters per second squared. Okay, that's what they got. So we did right. Okay, let's look at the next one. See where this takes us. So I think very similar to what we just had. So we've got, once again, a spindle of some sort of materials, not sure. We know the radius of the sink, and we know the mass of the sink is big M. I need to draw one of the sides a little bit better for this, what we're doing to make sense. So let me try and make that more circular. Okay, so this is R, we know R. The material, the spindle, is hanging down like this, and it's holding up a box of mass, little m. That box is going to fall a height, h. We know the mass of this sink. This has mass big M. Once again, we know moment of inertia. Then it's going to be 1/2 big M R squared. Right?
Yeah.
Okay.
We're supposed to find the tension in the string pulling up on the sink.
Okay.
So we'll call that T, the tension.
How do you find tension again?
Tension's a force, mass times acceleration.
Oh, I see.
We need to find the tension, and we need to find, so we're looking for tension is equal to, and we're looking for tangential acceleration. No, not alpha. Tangential acceleration, what this is equal to, right?
Okay.
Okay, and we're looking for these things when the box has fallen some distance h. H might have been a meter, h might have been 10 meters.
Yeah.
We don't know. So we're keeping it very general so that you can plug in any numbers. We don't have any numbers for this problem. We're just going to give equations. Good?
Mm-hmm.
Okay, so the fact that I have a box falling some distance begs for me to somehow bring energy into this equation, right?
Energy.
Energy, yeah.
Aren't you just looking for acceleration?
I mean, the acceleration of the thing is going to change with time.
Yeah, with time, but isn't the formula just mass times acceleration?
Well, where are you going to go with that?
Well, if it's going directly downwards, then that's just gravity.
But it's being resisted by this thing.
How is it being resisted by it?
Imagine that you are, I don't know, trying to not missing anyone.
Not missing anyone?
Correct. Let's think about some intuitive way to make this make sense. That it's not going to be in free fall. So imagine that this is like a hose wound up on some big coil,
Okay, I see that.
right? And somehow it's up in the air and you hang on the hose as you fall. Are you going to fall slower as you uncoil the hose?
No.
You have to. Some of your energy, some of the energy that comes from that object falling has to go into rotating that thing.
Oh, that makes sense.
Okay. Well, I was trying to, how can I make this make sense without bringing energy into it? So, yes, this problem is begging for energy to come into it. We have some energy being introduced to the system as this thing falls from here to here. And some of that energy has to go into rotating this. So, this object is not in free fall.
So what's the tension for formula then? Sorry.
We
what's
got
the
to figure
formula
that
for
out.
tension?
There isn't just some formula. Here, plug into this and you get tension. All I know is that the net forces acting on the thing is equal to its mass times its acceleration. So here's what I know. I know looking at this thing, its mass times, and its acceleration is going to be tangential acceleration. Tangential acceleration is equal to the sum of all the forces acting on it.
How do you know it's tangential acceleration?
It's going
This can't accelerate any faster than this thing's unwinding.
Okay.
Okay. So its mass times its acceleration has to be equal to the sum of the net forces on it. The sum of the net forces on it are going to be its weight. I may call this the positive direction, so tension is going to be in the negative direction, minus tension.
Okay.
So that's going to be the sum of the forces acting on that thing.
So it's just.
So there's one equation that we're going to need that has tangent and t. Notice that those are the two things we're trying to find. So we're going to have to come up with two equations with two unknowns. I was going to do this one second, but we can do this one first.
Okay.
Okay, now we got to get our second equation.
Then you're just trying to look for tension, right?
It's going to be a second equation that somehow relates tangential acceleration with tension.
Yeah, I'm saying, wouldn't you try and find tension, and through using that equation you can then find...
Sure. Once I have two equations, I solve one equation for one of my variables, plug it into the other equation. That's trivial once we get our two equations with the two unknowns. The hard part is coming up with our two equations. So there's one equation. What's the other equation I'm going to use that has a tangential acceleration in it and a tension in it?
Your kinetics and potentials, right?
Right, so this is where energy comes into the picture. So I was going to derive this equation first and then this one second, but it doesn't matter what we're going to do it in. So here's one equation that we're going to have to use.
Okay.
And now going back and thinking about the energy in the system, let's think about the energy that goes into the system. What do I always and forever know? Let's write the always and forever equation down here for a second. We always and forever know that U1 plus K1 plus the work that goes into the system is equal to U2 plus K2. That's your always and forever equation. Okay, so thinking about the energies now, what's our potential energy at the start of the system?
MGH.
MGH, you following that?
Mm-hmm.
Okay. So we have MGH. I'll write my final equation. We're going to have to play with this one, so we'll come down a little bit and then go back up there and write it. MGH plus, what's our kinetic energy at the start of the system?
Nothing.
Zero. Nothing. What's the work that goes into the system?
Nothing.
Isn't it just
Nothing.
MGH?
That's part of the system. Work going into the system would be if I take my hand and I tug down on the box now.
Oh, yeah. That
The
makes
box attached to this is the whole system. So how the system changes isn't work going into the system, that's just the system changing.
sense. Okay.
So there's no work going into the system. So our total potential energy at the start is just MGH. Right?
Yeah.
Okay. Now this is equal to, what's our potential energy at the end?
You don't have any.
We don't have any. What's our kinetic energy at the end?
1/2
1/2.
mv squared.
1/2 mv squared. Is that it?
That's it.
What energy is this accounting for? Tell me physically what this represents.
That's the energy
It's the energy that went into falling.
of it spinning.
No, this is the energy of that falling object. We haven't accounted for spinning yet.
Oh, so how do you account for spinning?
So here's the energy of this box falling, because as this box falls, it speeds up, right?
Yeah.
This box has kinetic energy. Now we also got to account for the kinetic energy of this thing. What's its kinetic energy?
All the masses times the radius is squared.
1/2 I omega squared. What we came up with last week.
Oh, yeah.
Yeah?
Wait, would it be minus it from your...
No. That's everywhere that the energy went.
Yeah, but isn't
This
the
isn't a
second part
negative.
resisting it?
Just think about where the energy went. So before I had this gravitational potential energy, right?
Mm-hmm.
Afterwards, I lose that gravitational potential energy when the box is down here. Right?
Yes.
Where'd the energy go? Some of the energy went into speeding up this box. So now the box has speed. And some of the energy went into spinning this. So now that thing's spinning.
Oh, I see.
Just track where the energy went.
Okay.
The notion of negative energy will confuse the holy bejesus out of you. So don't try to think that way in terms of, oh, it's resisting, that's a negative energy. Anything doing negative stuff like that, we always account with just the work right here, going into or out of the system.
Okay.
So some of the energy goes into that, some of the energy goes into moving this, and that's everywhere the energy goes. Right?
Mm-hmm.
So there's our second equation. Let's manipulate this equation now to make it more useful. Rewrite it really quick a different way. So we have MGH is equal to 1/2 mv squared plus, expanding out this, I was 1/2, right?
Yeah.
So we have 1/4. Capital M, remember there's a difference between capital M and little m. Little m is the mass of that, capital M is the mass of that. So 1/4 m r squared times omega squared.
Mm-hmm.
right?
Okay, but that doesn't have tension or tangential acceleration in it.
But the first one does.
We'll get tangential acceleration out of this.
Here we go.
Well, somehow. I'm not sure how yet. We'll figure it out.
Well, how do you get tangential acceleration out of just energy?
Let's think about this. We can get our velocities. Find mg. That's not very useful. We are missing something obvious. I'm just not thinking of it. Oh, I don't want to do that. That might work. All right. Let's peek at the book's idea. So we've got that equation. We did that. Let's see, for torque, okay, we're not going to use energy at all. Let's go down a bad path. So we think about the forces, now let's think about the torques. That's the way that they're going to say this. Let's think about the torque on the system, on this system, because we also know that the sum of the torques on the system, the total torque on the system, is equal to its mass, not its mass, its moment of inertia, times its angular acceleration, right? Same way we have F equals ma, we have the total torque on this is equal to its moment of inertia times its alpha. Now, what is the torque on that going to be? What's the force that's going to create torque here?
The force?
Remember, another way that we represent torque, this is also equal to some force times r times the sine of the angle between them. Right? What's the force that's producing torque here?
Just tangential force.
Oh, I thought you had it.
Okay.
What is causing this thing to rotate?
Gravity.
Gravity is pulling this box down, right?
Yeah.
Gravity is pulling this box down, so that's creating a force here. How is that force, the force of gravity on this, communicated to this thing?
Through the tension?
Through the tension. Tension. If T is pulling up right here, T is pulling down right here. Equal and opposite.
Yeah.
So we have the force of tension here times R.
All the force is the tension?
That is the only force causing this thing to spin, is the tension in the cable. If I cut the cable, that thing wouldn't spin.
Okay.
Make sense?
Well, where's your sine of theta?
It's at a right angle.
Oh. Yep, that makes sense.
Okay. Good?
So T is equal to I. No, it's not.
Now T is equal to R.
So we can say T is equal to I times alpha over R.
Yeah.
Right?
And you can take an R out of the I.
Let's see. With our alpha, was an alpha one of the given properties? Oh, alpha is one of the things we're finding. Oh no, I'm looking at two different problems. But alpha was not given to us. So let's just write this out really quick. I know T is equal to that, so coming and plugging in up here, I know m times our tangential acceleration is equal to mg minus t. Right?
Yeah.
Well, maybe our alpha will go out as we plug in some of these things. So I'll just plug in my moment of inertia and keep playing with it and see what happens. So I get m times my tangential acceleration is equal to mg minus, we have 1/2, I'm going to put just a 2 in the bottom instead of the 1/2, you with me?
Mm-hmm.
1/2 big M alpha times r squared.
You can get rid of an r.
Wonderful. And can you see what else I can do? What can I do with the other r?
You can make acceleration out of alpha and r.
Perfect! I can make acceleration, my tangential acceleration, out of alpha and r. So this is equal to mg minus m times tangential acceleration over 2. Did we do that right?
Mm-hmm.
So I need to get this, both tangential accelerations on the same side. So I'm going to move this term over here. So I have a tangential times m plus big M over 2 is equal to mg. Did I do that right? Do you see what I did?
No, I don't.
I'm moving this term to the other side
Oh, and then distributing.
and then pulling out that a tangent. So when I pull a tangent out of this, it just leaves an m. When I pull an a tangent out of this, it just leaves an m over 2, and it's plus now since I moved it to the other side.
Yeah, I see it.
Good now? Okay, and then the author's probably going to divide both sides by m, little m. So we'll end up with a tangent times 1 plus big M over 2 little m is equal to g. And then finally we get a tangent is equal to g over, just trying to write it the exact same way he does. We're going to be basically the same way he does. He just leaves it just like that. So 1 all over 1 plus big M over 2 little m. Follow that?
Mm-hmm.
Yeah.
So there's our tangential acceleration. And then now we need to find tension. Once we have tangential acceleration, we can go back and plug it in to find tension from the top equation, right?
Okay.
So then tension is equal to, move tension to this side and this to the other side. Tension is equal to, factor out the mass, and we have g minus tangential acceleration.
Okay.
You follow what I did there?
Mm-hmm.
Yeah.
Okay? And I don't know that's worth plugging all that in. We plug it in and see what it reduces to. We'll come plugging up here. So then we get T is equal to m times g minus tangential acceleration, which is g all over 1 plus big M over 2 little m. And we could do a lot of simplifying potentially. See what he does here. What did he do? He had mg minus m times that whole thing. Okay, we have that. Going from here to here. Maybe he's just skipping a lot of algebra and expects us to just do it. But if we're going to do that, we should have got this common denominator. Looking at this term really quick, I can rewrite just that as 2m plus big M all over 2 little m like that. this is the same thing as what I have written in the denominator there, right?
Yeah.
So I can rewrite T is equal to M times G minus G over 2M plus big M all over 2 little m, right?
Okay.
And now we'll get a common denominator between these two terms. So I'll multiply G here by 2M over 2M plus big M. So scribble up here really quick. What's the best way to do that? Maybe before we do that, think about this divided by this is the same thing as this times the reciprocal of that, right?
Yeah.
So that's going to be, when I divide by reciprocal, we're going to have G times 2 little m all over 2 little m plus big M, right?
Okay.
So that's rewriting this term. So we can say T is equal to M times G minus 2 little mg all over 2 little m plus big M, right? Now get common denominator, so multiply this one top and bottom by 2 little m plus big M. So when I multiply G by 2m plus big M, we're going to get 2gm plus G big M. That will be the numerator for this term. We'll have 2gm, we'll have negative 2mg. So that and this term are going to cancel out. So when that's all said and done, we're going to have m times G big M over 2 little m plus big M, right?
Mm-hmm.
And then you can distribute the little m through.
Well, doesn't it just cancel out?
No! 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 You cannot cancel out that with that.
Why not?
You have to, look, you have to be able to rewrite it as a 1 to cancel it out. Which means I have to be able to factor a little m out of the bottom, and then I can cancel it out.
Oh, I see.
Which you can't do. Let's see. But he doesn't have the big M in the top, so he cancels that out. How he writes it, it doesn't really matter getting his exact equation. We have something logically equivalent there. I don't know why his is much cleaner than that. We could put the little m inside of there, and then there you have it. So, probably the way I would have had it is G times little m times big M. Yeah, something logically equivalent. I actually like ours better. No point going through the algebra once we're done with physics. But there it is, right?
Yeah.
There's our tangential acceleration. Here's the tension. So, give you some numbers, you should be able to figure out what it is in general. Okay, moving forward now. Rotation of a rigid body. So the next concept we're going to be talking about, and we'll move over to the whiteboard, so let's move the camera. But the next concept we're going to be talking about is the rotation of a rigid body, and the energy now in the rotation of some rigid body. Rather than using oversimplifications that we've been using thus far, still can't see. Jeez. So, kinetic energy inside of a rigid body. Let's get you a feel for what it is we're trying to calculate. Here I have some rigid body, and it's flying through the air. So the dotted line is showing the path that the thing's following.
Okay.
So some rigid body flying through the air, and while that rigid body is flying through the air, it also is rotating some.
Okay.
You with me? Mm-hmm. So omega is the speed that this thing's rotating, whatever that is. Here's its center of mass. And we found out last time, not last time, but a couple times ago, that the velocity of center of mass is the same thing as for each mass, for each little mass, add up its, we figured out how to calculate the velocity of the center of mass. The velocity of the center of mass, just to remind you, velocity of center of mass was equal to the velocity of particle 1 times the mass of particle 1 plus the velocity of particle 2 plus the mass, or times the mass of particle 2, dot, 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 all over the mass of 1 plus the mass of 2, dot, 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 right?
Yeah.
It was just a derivative of the center of mass. Center of mass, if we were talking about in the x direction, x center of mass was going to be x1 times m1 plus x2 times m2, dot, 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 all over m1 plus m2, dot, dot, dot. Take the derivative of this with respect to time, you get that. Because all the masses, they're just constants.
Yeah.
Okay, so that's how we got, that's what we meant by the velocity of center of mass. Here's its exact definition. And so the whole object, when you view the center of mass as an object, it follows this velocity of the center of mass.
Okay.
So if all you care about, if you're just trying to track the trajectory of some rigid body object through the air, something like this marker, you just need to know its center of mass, and its center of mass is going to be the point that perfectly follows a parabola as it falls through the air. Notice that the whole marker doesn't perfectly follow a parabola, because the marker might be spinning some as it falls through the air. And so if you follow some individual point, it might be doing something like this throughout the air.
Yeah.
But if you look at the center of mass is going to be the thing that perfectly follows that parabolic motion as this thing falls through the air. I don't know if I can give you a demo. You can probably see a marker spin through the air. So I'll just toss this marker ball and intentionally give it a spin. And you'll notice it still follows a parabola, but it's going to be spinning. So it's the center of mass that was following a parabola. And you notice, if we had a big enough object, its center of mass would be the thing that was easy for your eye to follow through the air, if you had something long enough.
Okay, that makes sense.
I don't want to check that. I'm afraid I break it. Need like a yardstick. Don't have a yardstick in here? Anyways, oh yeah, we do. Now I wonder if I could give this thing enough of a toss without hitting the ceiling. That was a terrible throw. Can't get a good spin. Is that worth going outside and seeing, or do you think you got the point?
I doubt it.
All right. So we can just follow the center of mass. So how the center of mass follows the normal trajectory. And so the velocity of the center of mass is what we mean by how fast is that object moving. The whole time so far we've been talking about how's an object moving, we've been pretending that the whole object was just concentrated at center of mass, and talk about how center of mass is moving is how the whole object is moving, right?
Yeah.
That's what we've been assuming so far. Now we're going to be a little bit more precise and point that out. What we've always been talking about when we said how fast an object is traveling, we meant how fast the center of mass of that object is traveling. And so the velocity of the object has always meant the velocity of its center of mass. Good? Now we want to talk about the energy that this object has. The energy in its motion, we're talking about kinetic energy here. The kinetic energy of this object. Because notice that this object gets kinetic energy from two places. It gets kinetic energy from the fact that it's flying through the air.
Yeah.
And it gets kinetic energy from
Spin.
spinning. So your intuition should be screaming, the total kinetic energy of this should be something like 1/2 its total mass. We'll use big M for its total mass since we're adding up a bunch of masses.
Okay.
Times the velocity of its center of mass squared. The magnitude of that velocity, right?
Yeah.
Plus 1/2 its moment of inertia, whatever that is, times omega squared. For the fact that it's rotating.
Yeah.
That is what your intuition should say. That is what we hope the kinetic energy of the system is, right?
That we hope it is.
Yeah, we're going to prove that that's the case.
Oh, I see.
But intuitively, here's the result we expect, and we're going to prove that the result we expect is the correct result. You with me?
Yeah.
Okay, so let's follow through on this. What's our ultimate strategy going to be? Our ultimate strategy is we're going to pick some point mass, little m sub I, on that object. We're going to calculate its kinetic energy. You with me?
Mm-hmm.
And we're going to do that for every little m sub I, calculate all their individual kinetic energies, add up all the kinetic energies, that's the total kinetic energy. And the total kinetic energy is going to come out like this.
Gotcha.
Good? Feel like you understand our overall strategy?
I think so.
Okay. Now, there's going to be a useful substitution for us as we're talking about this. We're going to use v sub I to be the velocity of that little point mass. Notice the velocity of that little point mass is kind of a complicated thing. Because the velocity of that point mass, it might be pointing in some weird direction because remember, there's a velocity of how the object's flying through the air, but then that thing's also spinning. Think about the velocity of the very tip of this lid as it falls through, as it travels through the air. It's all over the place, right? Because even though the object is traveling forward, since the object's spinning, the lid might actually have a velocity that way for a moment. Does that make sense? So the velocity of some arbitrary mass, that's kind of a complicated thing to talk about. We're going to have to come up with a way to talk about that. But notice that it's not necessarily the velocity of the center of mass. You with me? Okay. So we're going to come up with v sub I prime. V sub I prime is going to be the velocity of this mass, of this point mass, relative to the center of mass.
Relative to the center of mass.
Relative to the center of mass. So relative to the center of mass, if I glued you right into the center of the mass and you watch this particle moving, that's real simple. It's just moving in a circle around you.
Yeah.
Because the object's just spinning. So we're going to use v sub I prime to be the velocity of m sub I relative to the center of mass. How do we calculate the velocity relative to the center of mass? Well, let's not say that. So if v sub I prime is the velocity of this object relative to the center of mass, then we can represent the velocity v sub I, that object's total velocity, that's going to be equal to the velocity of the center of mass plus the velocity of that object relative to the center of mass.
Okay.
It's the exact same way that we said figuring out the velocity of someone walking on a train. I'll give you a really simple example of this really quick. So say that we're on a train, and the train is traveling this way with the velocity of the center of mass of the train. Right?
Mm-hmm.
Here you are, and you're watching me. I'm little m sub I. I'm little m sub I. Here I am. You're watching me, and inside of the train, not only I'm also moving with a velocity v sub I prime. My velocity is relative to the train's velocity. Right?
Mm-hmm.
So inside the train, here's my velocity. Here's the velocity of the train. What's my velocity to you? It's equal to the velocity of the train plus my velocity relative to the train.
Except this is in a circle.
But it doesn't matter. It's the same concept.
Okay.
I drew that my velocity is in a straight line here, but who knows? The point is, whatever my velocity is inside that train, if you know my velocity in the train, whatever it is, and you know the velocity of the train, then you now know my velocity relative to you outside the train, in your inertial reference frame.
Okay.
So the velocity of this object, whatever it is going to be the velocity of the center of mass plus the velocity of this object relative to the center of mass. Does that make sense?
Yep, that makes sense.
Okay, so that's what we're saying here. V sub I prime is going to be the velocity of the point mass relative to the center of mass. So the velocity of the point mass is equal to the velocity of the center of mass plus the velocity of the point mass relative to the center of mass.
Mm-hmm.
Think we're good with that substitution? Okay, so just note that. We'll use that here in a second. Now let's go back to our ultimate strategy. What was our ultimate strategy? The total kinetic energy then is equal to the sums of all the kinetic energies.
Yeah.
Mm-hmm.
And I'm going to draw up using this little sub I and this n up here and just start writing sums. And expect you to know what I mean when you see a sum with a k sub I.
Okay.
Okay, so we're going to sum up all the individual kinetic energies, where what is one of those little k sub i's?
It's the mass times the radius squared.
No, it's 1/2 mi times vi squared. This is always how you calculate kinetic energy for a point mass. It's this. When
And
we
how
came
about your AD or kinetic
when
energy?
we came up with k is equal to 1/2 I omega squared,
Yeah.
we did a similar thing. We added up all the point masses traveling perfectly in a circle, this exact way, and the sum came out to that.
Yeah, but the sum
But we
was-
calculated it this way. This is a sum for an entire object.
Okay.
We have an entire object rotating.
Yeah.
We do not have an entire object rotating anymore. We just have that little point mass moving.
In a circle.
But every mass is different.
The moment of inertia, if we were to calculate the moment of inertia traveling in a circle around that thing, we could do that. But then that just gives us its mass from traveling in a circle around that thing. This thing has a weird velocity. It doesn't just have a velocity traveling in a circle, because that object's also flying through the air. So its velocity is some random velocity. We don't know what it is.
So it's not just traveling in a circle?
No. The tip of this marker is not just traveling in a circle.
For sure?
It was like right here, right here, right here. That's not tracing out the path of a circle. It's like doing a loop-de-loop parabola.
Yeah.
If I were to draw the path of that thing, that's like, I don't know. It's definitely not a circle. It's all over the place. If it was traveling in a circle, it'd look like this. Look.
No.
It's traveling in a circle relative to the center of mass.
Yeah.
Yes. But what's its total velocity? What's its total kinetic energy?
Well, why do we care about velocity if we're looking for kinetic energy?
Most basic definition of kinetic energy. Look, here's the definition of kinetic energy for a point mass. For a point mass, kinetic energy is 1/2 mv squared. Always and forever. We found out using this definition that it just so happens that the kinetic energy for a large object is also 1/2 I m, or 1/2 I omega squared, where that object is traveling in a circle. This being true implies this is true. This is not the definition of kinetic energy. Here's our definition. Using this, when we took an integral across an object, we got this for an object that's just rotating.
Okay.
We no longer have an object just rotating. We got some weird object that's flying through the air and spinning.
And you're saying the second equation doesn't work?
We can't just assume we can use this. We're hoping that this shows up in our final answer right there. But we got to prove that it shows up in our final answer.
Oh, we're proving that works.
Yes.
Okay.
So we got to go back to our basic definition of kinetic energy. The kinetic energy of a point mass is this, by definition.
Okay.
So when we're talking about the kinetic energy of just that one atom on this thing, then here's the equation that we're going to use.
Okay.
Make sense?
Yeah, that makes sense.
Okay. Yeah, it can get confusing going back and forth. Because you see that rotation and you instantly want to start thinking moment of inertia.
Yeah.
But now we're just talking about one little atom flying through the air. Okay, so that one little atom flying through the air, here's its kinetic energy. Good?
Mm-hmm.
Now we got to go back to a dot product for a second. Hopefully you don't mind dot products.
Isn't it just the vectors multiplying each other?
The dot product, so if I have V1 is equal to X1 comma Y1,
Yeah.
and V2 is equal to X2 comma Y2, then the dot product, V1 dot V2, is equal to X1 times X2, so the dot product between vectors, those were vectors, vector, vector, so that we don't get confused when we're talking about times and dot product. Here we're talking about dot product, over here we're just talking about numbers, so we're just talking about times.
Yeah.
Plus Y1 times Y2, right?
Yeah.
So now let's think about taking the dot product of a vector with itself. When I take the dot product of a vector with itself, if I just do V1 dotted with V1, what do I get? I get X1 squared plus Y1 squared, right?
Yeah.
Where what is X1 and Y1? Let's draw V1 right here. If this is my V1, X1 is this, and Y1 is this, right?
Okay.
You with me?
Mm-hmm.
And so, X1 squared plus Y1 squared, that's the same thing as the hypotenuse squared. So this is equal to the magnitude squared.
Because of the Pythagorean Theorem?
Pythagorean Theorem.
Okay.
This side squared is equal to this side squared plus this side squared. Which
Yeah.
is exactly what I have written right there. You with me? So when you dot a vector with itself, it gives you the magnitude of that vector squared. Follow that?
That makes sense.
Okay, that's a little bit that we're going to have to use here. So I wanted to especially point that out. So just make sure it's clear in your mind that VI dotted with VI is just VI squared.
Okay.
Okay, so we're going to take this now, and I'm going to rewrite it like this. So K sub I then is equal to 1/2 M sub I, and instead of writing VI squared, I'm going to write VI dotted with VI. We're talking about the vectors.
Okay.
You see that substitution? Okay, now we're going to use this substitution. Notice VI is equal to the velocity of the center of mass plus the velocity of I relative to the center of mass. So I'm going to use this substitution now. So that's what I do going from here to here. Okay? That's still a dot product. When I add two vectors together, I get a vector. When I add two vectors together, I get a vector. So this is still a dot product of two vectors that we add together.
But all in all, you should come up with one number, right?
Yeah, when it's all said and done, we're going to come out with just a number because energy is always measured as a scalar. You can't talk about energy in a direction. Okay, so now I'm just going to calculate the dot product between these. Okay? So first I'm going to have, it's just like regular distribution. I'm going to have this dotted with this.
Okay.
That's right there, VCM squared. Notice that when you take a vector and you dot it with itself, it just gives you the magnitude square.
Yep.
And then I'm going to have this dotted with this, and this dotted with this. Those are both the same. Velocity of center of mass dotted with V sub I, and V sub I dotted with the velocity of center of mass. So we're going to have two V sub I primes, those are both prime. V sub I primes dotted with the velocity of center of mass.
Okay.
And then finally I get V sub I prime dotted with V sub I prime, which is going to be V sub I prime squared. You follow that?
Yep.
Okay, so if that's what the kinetic energy of one atom is, right there, then when I add them all up, or when I get the total kinetic energy, I just need to add them all up.
Yeah.
So total kinetic energy is going to be, and I'm going to break this up into several sums as I do it, to go with. I'm going to sum up all these terms, that's right there. Then distributing that, sum up all those terms, that's right there. Then distribute that to that, sum up all those terms, that's right there, for the total kinetic energy.
Okay.
You still with me? Okay, now going back to a reminder of our velocity of center of mass. Remember that the velocity of the center of mass is equal to the velocity of 1 plus the velocity of 2 plus the velocity of 3 times the mass of 1 times the mass of 2 times the mass of 3 divided by the total masses, right?
Yep.
That was the definition of velocity of center of mass. Or in other words, if I, first off, the sum of all the masses, we usually use big M to represent that. So the denominator here is big M, and I'm going to move that to the other side. Multiply both sides of this equation by all the masses. And so on the left-hand side, we have VCM times the sum of all the masses. Good? And on the right-hand side, we just have the sum of all these terms up here.
Okay.
You with me? Let me point out where I'm going to go. So come back to this line for a second. Here we have the sum of all the... This term is basically this term right here.
I see it, but how do you know it?
Well, I'm just pointing out big picture where I'm going.
Oh, so you're gonna show
Yeah,
us
so
how
this
you're
term
going.
is going to give us this term. This term right here, it turns out, is going to give us this term. And the tricky part is this middle term is going to go to 0.
Cancels out with this other?
Yeah, this middle term, in fact, is a 0. And so I'm going to point out that this middle term is a 0. And so, like, the next 3 lines are pointing out, hey, this middle term is a 0. Then we'll go back to just this term and this term to make them look like this.
I see where you're going.
You understand what I'm saying? So I'm going to point out that this term right here is a 0. How am I going to do that? I'm going to use my velocity of center of mass to create a substitution there.
Okay.
And then with that substitution, I'm going to produce a dot product that comes out 0. So I'm going to do some substitutions to show this comes out 0.
Okay.
Here's intuitively how we know it comes to 0. And in fact, I don't even need to worry about that. It's this thing that's going to come out 0. So even ignoring that right there. Just this sum right here is actually the 0. Multiplying by that is still just a 0. Because what this term actually is going to give me the total of mass times the velocity of the center of mass relative to the center of mass, which is 0.
That doesn't make sense.
Okay, we'll try and make it make sense. So, going to say that this term comes out 0. That's what we're after here, even ignoring that.
Okay.
Just these two together, when you sum them up, comes out 0. That's what we're going to show. So observe that, first off, the velocity of center of mass is equal to that sum over the sum of all the masses. Put all the sum of masses on the left-hand side and you're left with this equation right here, right?
Yeah, I see that.
Okay, so now with this equation, remember that v sub I, we have a substitution for that, right here.
Okay. Yeah, I see it.
Oh, sorry. This is just something we're pointing out. Now back to the expression that we're going to show 0. So I'm going to show that this thing right here is 0. So I'll start by rewriting that right here. I'm going to show that this piece goes to 0 now. You with me?
Yeah.
So this, substituting in v sub I prime, what's v sub I prime? V sub I prime is v sub I minus the velocity of center of mass. So I'm going to take that and substitute like that. You with me?
Okay.
Okay. Now, we can break this into two separate sums. I can do this times this term, add all those up together, and then minus what I get when I do this times this term. Add all those up together. So just break up the sum. You with me on breaking up the sum?
Yeah, but how does that equal 0?
One step at a time.
Okay.
Okay, now notice what we have right here. We have the sum of all the masses times their velocities. The sum of all their masses times their velocities is equal to the total mass times the velocity of center of mass.
Yeah.
This is the total mass times the velocity of the center of mass. Over here,
You got your words mixed up, I guess.
no, I didn't. Let's say that again. Notice that this right here, the sum of all the masses times the velocities, is exactly what we have right here,
Sum of the masses times the velocities.
which we've shown is the total mass times the velocity of the center of mass.
Yeah.
So right here, I have the total mass times the velocity of the center of mass.
Oh, I see.
Minus, what do I have right here?
K.
The velocity of the center of mass, that's a constant. I can pull that out. Sum of all the masses, that's a total mass. This is just a total of mass times the velocity of the center of mass.
Yeah.
So this minus itself, which is 0.
Okay, I see that. But with your 1/2 m sub I times velocity prime sub I, so you
You said 1/2 m sub I times my velocity prime at I.
square.
Oh, so it was like this?
No, there was still a vector. Oh, no vector. You just wrote a vector over above it. Look at right above your observe that implies K right there.
You're saying right here?
Yeah, that part. How does that not equal 0? The last part of it.
This?
Yes.
Why would that be 0?
Well, your middle part is equal to 0. So I'm just trying to see.
Oh, sorry. That should be there. That's a magnitude. Our dot product's gone.
Okay, that makes sense.
Yep, good catch. Yeah, because that came from right here. Which came from dotting this with this, which just gives us the magnitude squared. Okay, yeah, good catch.
So it's the fact that the velocity prime is a vector that makes it go to 0, right?
Here's intuitively why is this 0. This sum right here, with how we defined, so we're looking at m sub I times v sub I prime as a vector, right? This is the sum that's going to be 0. This sum is going to be 0 every time intuitively, because what is v sub I prime? It is the velocity of that particle with respect to the center of mass, right?
Yeah. Yeah, that makes sense.
And so when I add up all the velocities of all the particles with respect to the center of mass, it's just going to give me 0. Their total velocity with respect to the center of mass is 0.
Why? Because there's like an opposite one on the other.
The sum of all the velocities is already the center of mass. How do I get the velocity of the center of mass? I sum up all the velocities.
Yeah.
So when you sum all the velocities, you already get the center of mass, right?
Okay.
So if my v sub I prime, so when I sum up all these, I get the velocity of the center of mass, right?
Yeah.
So when I sum up all those, I get the velocity of center mass is equal to, when I sum up all the velocities of center mass, I get the center of mass, plus, that now term has to be 0 when we sum them all up.
Oh, I see it. That makes sense.
If I add up so the sum of all the velocities with respect to the center of mass, when you sum them all up, is always going to come out 0. For every velocity I have going that way, I may have one going that way. For every one I have going that way with respect to center of mass, I may have one going that way.
But it's a rigid body, so it's not like exactly.
It's a rigid body, but when I add up all the velocities, in the aggregate, everything's just following the center of mass.
That makes sense.
So when you add up all the velocities relative to the center of mass, it's 0, because they're all, in the aggregate, just following the center of mass.
Yeah. Even though it's spinning?
Even though it's spinning. Anytime, intuitively, anytime this thing has a velocity going backwards, this thing had a velocity of that same speed going forward.
Oh, because they're all following the...
Because they're all just following the center of mass. And so if I add up all those velocities, it's just going to be the velocity of the center of mass. So if I add up all those velocities with respect to the center of mass, it's going to be 0. Because they're all just following the center of mass.
Okay. I got
It's like a billion people, add up a billion people moving around inside of this. Well, that's not a rigid body anymore, so that doesn't work. So can't use that example. Have to use a rigid body. Anyways, yeah. So we showed you the algebra, why it comes out 0. Tried to make the intuition click, why it comes out 0. But either way, this middle term right here comes out 0. So we're left with this sum and this sum, right?
Okay, so now, how does the right turn equal moment of inertia?
So let's go down and rewrite what we have. So now we're going from here to here. Center of mass is a constant. Velocity of the center of mass is a constant, right?
Velocity of center mass is constant?
Yeah. At some instant in time. It's going to be, each little mass has a different velocity. But the velocity of the center mass is the velocity of center mass.
Yeah.
That doesn't change depending on which m sub I I'm talking about, is what I mean by constant here. Because
Okay.
we're summing over all the little m sub i's. The velocity of the center mass doesn't change. That's what I mean, right?
In a specific moment of time.
In a specific moment of time, yeah, when we add up, here's the best way to say it. The velocity of the center of mass doesn't change as we choose different point masses to talk about.
Okay.
That's the way to say it, because we're adding up across point masses. So adding up across point masses, the velocity of the center of mass doesn't change. So I can pull this to the outside.
Okay.
And the 1/2 I can pull to the outside.
Okay.
So then we're just summing up all the little masses, the m sub i's, that's what we mean by big M.
Gotcha.
So this turns into this. You good with that?
Mm-hmm.
Plus 1/2. So for this term, I'm just pulling out the 1/2 so far.
Okay.
Keep doing that. And we don't need that. Geez, did I just put vectors everywhere? Sorry. Our vectors are gone. We don't have vectors in here. We just have scalars.
Okay.
That was carryover from when I had my mistake there. Anyways, so we've gotten down to this equation right here, right?
Okay.
And we're good with the left-hand one. It's just this one that we still need to work with.
Mm-hmm.
Okay. Now we're looking at another way to think about v sub I prime. V sub I prime, since it's the velocity of this mass relative to the center of mass, that's just its rotational velocity, the velocity going into the fact that it's spinning,
So omega?
times
Radius.
r.
Of the individual.
Omega times r gives you your spinning velocity.
That's right.
Okay, so that's what we're going to do as our next substitution. We're right here, I think. So I'm going to replace v sub I prime with r sub I times omega. The radius to that point times omega. Notice omega is a constant for the whole object. The whole object spins at the same rate.
Yeah.
So omega is the same for everyone. But the radius to a point is going to vary from point to point. Good?
Yep.
Okay? So now, take these two terms. Now they're right here. Going from here to here, what am I going to do? I'm going to square each of these terms. So we have r sub I squared.
And then n times r squared.
sub I times r sub I squared is exactly what we mean by moment of inertia.
Sub I.
At that, for that point, yes.
Yeah.
And then the omega squared right there. Good?
Yeah.
Alright? And then sum up all the, notice that omega squared doesn't change from point to point. Omega doesn't change from point to point. So we can pull that outside the sum. And so now we use capital I to represent the sum of all the moments of inertia. And there we go. Okay. Follow that? Bit dense.
A little bit.
Now, I debated not going through this with you guys because I thought this was intuitive enough that we could probably just be on our merry way. So the point in going through this wasn't so much to see the physics of it as to get you comfortable thinking about how we do these types of physics proofs. Go back to thinking about points of point masses, because this was like a similar thing that you had to do on that extra credit problem for coming up with the kinetic energy in a spring, right? It's the same type of thing. Break down the problem, think about a single point, calculate the energies for that single point, add up all the energies.
Is that all the material for the chapter?
No, we haven't even gotten to angular momentum yet.
Angular momentum.
Angular momentum.
Jeez.
Yeah, maybe we'll skip over some example problems that try to cover material so that you can get started on material and then go back. So the next couple things that we want to prove then is the work done by a torque.
Torque does work?
Yeah, let's think about it for a second. So I know that work, one of the most general ways that we've been talking about work, is going from some point x1 to some point x2 and summing up all the little works you do from going from x1 to x2.
Okay.
Right?
Yeah.
That's the simplest way to think about work. Now let's think about it in a special case where it's like torque and there's a rotation. So in the special case where there's torque and there's a rotation, our x1 might be somewhere right here and our x2 might be somewhere like right there, right?
Yeah.
So rather than calling that x1 and x2, we can have an associated theta with it, and we can call it theta 1 and theta 2, right?
Mm-hmm.
And we can still sum up all the little bit of works that we do. And we'll still get the same thing.
The same thing, even though you...
Yeah, now we're just summing up all the little works from this angle to this angle rather than from this point to this point. It doesn't matter how we signify our start and end points, they're still the same points.
How do you account for the r, the radius?
Well, how you actually calculate this integral, if I calculate this integral, I need a dx to show up somewhere here.
Mm-hmm.
If I calculate this integral, I need to rewrite this out. A d theta shows up there. So it's just rearranging the terms so that a dx shows up rather than a
D theta.
d theta, or vice versa.
Okay.
So there's a lot of ways that we can calculate the dw, because we know that one way that we got work is it was equal to force times distance, right?
Yeah.
Yep.
And so one of the ways that we can represent dw is we can represent it force times dx.
Force times dx.
For a dw, for
Oh,
really,
for the little tiny, okay.
for the little tiny infinitesimal change. So here's one way that we could have thought about that. So we could have thought about this as rather than dw, we could have thought about this as an f times dx, right?
Oh, that's what we're used to.
Yeah, that's what, okay. So then I could have also written this as the integral from, ignore the points for a second, but rather than dx, I could have said f times let me think for a second. D theta times r is dx. Okay, that's what I'm thinking. D theta times r is dx, right?
Okay.
So I can put that substitution in here, and so now I can replace this with f times r times d theta. And now I want to go from theta 1 to theta 2 rather than x1 to x2, since I changed what we're integrating with respect to.
Yeah.
But we're still adding up the same values, right?
Yeah.
Still
that
the same
makes
integral.
sense.
Now, f times r, if we're talking about r always being on a circle, so that if f is always tangent to r, so that the f is always this way, perpendicular to it.
Okay.
If the F is always tangential to R, then we can just rewrite that Fr as the torque. Because remember, we wrote F dot dx, but that was where F is in the same direction as motion. Otherwise, we have to use the dot product.
Okay.
You remember that?
I think so. Can you remind us of it?
Here's exactly the perfect definition of work. Work is equal to the integral of the F vector dotted with the dr vector.
Yeah, I remember that.
And so when you're actually calculating work, the dot product gives you the component of F in the same direction as R. So the force has to be in the same direction as your work. If I said I'm pushing a box, and I'm pushing a box with a force this way, F, but it's displaced this way, I had to find the component of F that goes in that direction. Right?
Okay.
So maybe, to help make sense up here, I'll put F sub x there, to remind us that's the x along the path of our motion. You with me? And then maybe the F I put here, I'll put tangential F. And those would be the same thing.
Gotcha.
That's probably the best way to do that. You with me?
Okay.
Okay? Now, what is tangential F times R?
Just the tau.
Torque.
Torque, sorry.
Torque. So this is the integral from 1 to 2 of torque times d theta. And notice you could have almost guessed that from looking at this. Well, if we calculate work by doing a force times a distance, then we probably calculate work doing a torque times a theta.
Yeah.
Can you say that again? Just in simpler terms.
Let's think about calculating these integrals in really simple cases. Well, let's just calculate this. Assume f of x is a constant. So assume we're applying a constant force. What is this integral? If f of x is a constant, pull that out and just calculate the integral. So the work, in that case, would just be f of x times x2 minus x1. The force times the displacement.
Yeah.
Okay, if our tau is constant here, then what's our work? Our work is just equal to tau times our angular displacement.
Okay.
That's a parallel.
I see it.
The point is, the next thing you're going to have to do is calculate work done on these systems.
On systems where it's spinning?
Yes. Same way that you calculate works due to displacements, now you need to calculate works due to spinning. Or the works required to make something spin.
Okay.
Alright, let's see if I can come up with the other way that we're going to represent this integral. So I know that work is going to be equal to the integral from theta 1 to theta 2 of tau times d theta. The other way we could write tau is, so this is the integral. Tau, we also know that we can write that as a moment of inertia times alpha. We already proved that, right?
Yep.
D theta. Let me keep thinking about that for a second. Alpha, we know I can write as the derivative of omega with respect to time times d theta. We good with that?
Yeah.
I'm showing how the kinetic energy version of this comes out.
Okay.
We did something similar before where we said, notice that work is equal to also the change in kinetic energy, K2 minus K1. I'm going to do something similar with circular kinetic energy. At least that's what I'm trying to do. So then this is equal to the integral of, I'm going to move the dt over there, so I'm going to get I dw times d theta over dt. And what is d theta over dt?
It's just
Omega. Omega. So this now, notice that I have an integral in terms of omega now. So it's the integral of I times omega times d omega.
Okay.
Now when we calculate that integral from omega 1 to omega 2, because notice that's the variable we're integrating with respect to now.
Yeah.
what do we get? The moment of inertia, that's just a constant, that comes out. And so that's going to be equal to the moment of inertia times omega squared over 2, right?
Yeah.
Evaluated from omega 1 to omega 2.
Oh, I see.
Which is going to be 1/2 I omega 2 squared minus 1/2 I omega 1 squared. Or the change in angular kinetic energy, which is exactly what we hope for, right?
It's exactly what we hope for.
Yeah, we hoped that the work due to torque also gave us a change in rotational kinetic energy, the same way that work due to force gave us a change in linear kinetic energy. So more and more of these parallels. So that you don't have to overthink, over-memorize a bunch of different things for a bunch of different situations. And now the power. Let's see if we can get our equation for power really quick. Power, do we remember what power was?
Mass times velocity.
No, I know it also uses a P, sorry. Momentum uses a P and power uses a P. But just think intuitively, what is power? It's how much energy you use per second, right?
Yeah, it's joules over seconds.
It's joules per second, yes, exactly. So you calculate that by doing the derivative of energy with respect to time.
How do you do the derivative of kinetic energy?
Well, we do kinetic energy and work the same thing, so the derivative of work with respect to time.
Oh, that makes sense.
And so, when I do the derivative of work with respect to time, where work is equal to that, I need a time dt to show up. How do I get the dt to show up? Don't want to spend too much time trying to be clever about it. Oh, I'm way overthinking it. We probably already erased it somewhere, but looking at this, notice that I know that dw is equal to tau times d theta, right? Because work is equal to the integral of all the small works. Add up the infinitesimally many small works, that gives you the total work. Everything inside an integral is always just a differential of the thing you're adding, of the total thing you're adding up, right?
Okay.
So this is a bunch of different ways of writing dw. That's dw, that's dw, that's dw. Does that make sense?
Yeah.
So we're always doing that. So here's dw, and now I want dw dt. So I just put a dt at the denominator of that. And so we get tau times d theta dt, right?
Okay.
Which is equal to tau times theta, or omega. And you might remember that we had a tricky formula. We only used it like once or twice for calculating power last time, but it turns out it was force times velocity. So old equation, new equation, which we could have almost guessed at.
Yeah.
And you see how to get this from that pretty easily. Divide this by an r, turns it into an omega. Put the r over here, turns it to a tau.
Divide force by r?
No, divide v by r. Omega times r gives you v.
Yeah.
So v divided by r gives you omega. So divide this by r, and then put the r, and then multiply this by r. So we divided by r and multiplied by r.
Oh, so you're just times by 1?
I'm just trying to show you how these are intuitively related.
Okay, that makes sense.
Okay. And we still haven't gotten to angular momentum. I don't know. Sugar.
This is a lot.
It is a lot. But fortunately, it's a lot that's parallel.
Yeah, it's just making connections.
So maybe we'll roll over some into tomorrow. So I'll give you the quick of angular momentum. Then we'll let you finish on, give you the rest of the day, and tomorrow we'll re-pick up doing example problems. Because it is a lot, and I don't want you to lose angular momentum.
Is
It's
the
a crucial
material
concept.
for tomorrow short then?
Huh?
So is the material for tomorrow short for chapter 11?
I don't know, but we still have plenty of time in the semester. We don't need to rush it,
Okay.
so we can take a little bit of time to make sure things make sense.
Do you ever explain pulleys?
Explain what?
Pulleys.
Pulleys? Oh, did we skip over that?
Yeah.
Okay, we'll cover angular momentum. We'll stop and I'll quickly give you pulleys.
Please.
It's not hard, but it follows from the physics we've already talked about. Can't believe we didn't do an example with pulleys. I don't think we did. That's terrible.
Are you asking because of yesterday, Jeremy?
Yes. I want to figure
We
out.
went
how it
rock
works.
climbing and we couldn't figure out, why was it working like that.
Because you have someone who's super small holding a staff all the way at 50 feet with a pulley.
Yeah.
And I was like, that should just carry her.
Yeah, you should fall and choose your bow up. That's what I was thinking.
Okay, yeah, we'll go over, we'll answer some questions about pulley, but let me give you just the basics of angular momentum, and then we'll let you do it. So, the same way that we had regular momentum, now this is momentum, not power. Regular momentum, not power, was mass times velocity, right?
Yeah.
Angular momentum, L, is going to be cross product. Oh, sorry. Here's what I should have said. It's no wonder. I was trying to draw a bad parallel in my head. Okay, momentum, that was mass times velocity, that's fine. But let's think really quick. We said force was mass times acceleration, right?
Yeah.
But then we said torque. How do we get from force to torque? To get to torque, we took our force vector, we took our position vector, and we crossed it with our force vector. And that gave us like the angular version of force, which we call torque.
So you do the same thing
So,
for momentum?
similarly, with angular momentum, it's going to be our position vector crossed with our momentum vector, and that gives us our angular momentum vector.
Okay.
And so obviously another way you can write that is your angular momentum vector is equal to your position vector crossed with mass times your velocity vector. Same thing.
And the L stands for what?
Angular momentum. I know. Why L? Because we ran out of other letters and no one was ever using L.
Not even for length?
It's used for length a lot. It's just, I don't know how these conventions get adopted, but they do get adopted. And so similarly, the same way that we said that, the magnitude of torque was equal to the force vector times r times the sine of the angle between them.
Yeah.
Similarly, the magnitude of your angular momentum vector is also your momentum times r times the angle between them. And we don't usually use momentum equation like that. We usually write it as mvr sine of theta. Because momentum is mv.
Yeah, that
Mass
makes
times
sense.
velocity is momentum.
Okay.
Okay, now notice, let me raise some up here. Notice what happens when you took the derivative of momentum with respect to time. When I did the derivative of momentum with respect to time, that was equal to the derivative of velocity times mass with respect to time. Mass is just a constant, pull that out, so we get m times dv dt, which is equal to
Force.
mass times acceleration, or in other words, it's equal to force. So the derivative of momentum gave you force. What do we hope the derivative then of our angular momentum gives us with respect to time?
Your torque.
we hope that that gives us torque. So let's check to make sure that that gives us torque. So here's angular momentum, right?
Mhm.
So we need to take the derivative of that cross product. And that's going to be the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. Because we can take the derivative of both of these with respect to time.
Oh, I see what you mean. Okay.
Product rule for derivatives. Way
Yeah.
back, right?
Where you back?
Excuse me. Okay. So, what's the derivative of r with respect to time?
Of the radius? Isn't that just
Of a
radius?
position vector. Of our position vector.
Omega.
Oh, your position. It's just, yeah, omega.
What is the derivative of position with respect to time?
Velocity.
Velocity. R here is our position vector.
Oh, okay.
When we get rid of r, when we just do that, then that is the magnitude of our direction. When we're traveling in a circle, the magnitude of our direction is constant, and so it's just a radius.
When it's a vector.
But in general, this is just a position vector, r. Think about back to the Mars rover example that we did. We used
Yeah.
r to talk about its position.
Yeah.
That's what we mean. Just position vector.
Okay.
So here's your position vector. The derivative of your position vector with respect to time is
Velocity.
your velocity vector. So we get our velocity vector, the derivative of the first, crossed with the second, plus the derivative now of this one. What's the derivative of our velocity vector with respect to time?
Velocity.
Your acceleration.
Acceleration.
Acceleration. So we get
Force.
m times our acceleration vector.
Would that be a force vector?
Yep, that's a force vector. But just trying to make the algebra clear. So the derivative of the second crossed with the first. Ooh, I don't know if when I do a cross product I can switch their order like that. I think I have to keep the order the same. Because cross products aren't commutative, and we just think about it that way to memorize it. Sorry, let me make sure I'm not making a mistake there. It's been long since I've done Calc 3. So we have derivative of that times that plus, yeah, you have to maintain the order. So you can't change the order of these things, but the chain rule is the same. So we did the derivative of the first crossed with the second. Now we need to do the first crossed with the derivative of the second. Same thing, just keeping the order consistent. You with me?
Yeah.
Because remember, if we flip the order around with cross product, then it gives us negatives. So cross product is an example of an operation that's not commutative. Right?
Interesting.
So cross product, and now we need to do the derivative of the second one, right? Like that. Good?
Mm-hmm.
Now notice that m here is just constant, so kind of ignore that for a second. We have a vector crossed with itself.
Which is just the magnitude of velocity.
No, that's dot product.
Oh.
Cross product, to get the magnitude, you multiply by the sine of the angle between them. What's the angle between this vector and this vector?
0.
0. What's the sine of 0?
0.
0. So this term comes out 0.
Oh.
You with me?
Yeah.
How do you find the sign?
Huh?
Why are you trying to find, or the distance between them?
So when you calculate a cross product, we got it written somewhere. I don't know where we have it written. Oh, torque. Torque, so one definition of torque, the basic definition of torque is your torque vector is always equal to your position vector crossed with your force vector. That's its definition. When you're calculating the magnitude of a cross product, you can take the magnitude of this vector times the magnitude of this vector times the sine of the angle between them.
Yeah.
That's from chapter 1. So the magnitude of this vector, of the cross product, is going to be the magnitude of this vector times the magnitude of this vector times the sine of the angle between them.
Okay.
The angle between them is 0. The sine of the angle between them, or the angle between them is 0. So the sine of the angle between them is 0. So the magnitude of this whole vector is 0.
Mm-hmm.
So this whole vector is a 0 vector. So this is just equal to 0 vector. When you add that to another vector, it just gives us the other vector. So it's just going to be equal to this vector. Because this whole thing goes out to 0. You with me?
Mhm.
Yeah.
Okay, now let's look at what this vector is really quick. As you just said, oh, that's a force, isn't it? And by definition, your position vector crossed with your force vector is your torque, which is what we were hoping for.
Yeah.
The change in linear momentum with respect to time is torque.
Fun.
We got that, we got that. One more thing that we hope linear momentum has. Notice that, I don't know if I already wrote it over there somewhere, but remind ourselves of it one more time. Notice one more time that momentum was just equal to mass times velocity. So angular momentum, what would you hope that it would be? Instead of mass, you want
Your moment of inertia.
moment of inertia. And instead of velocity, you want
Omega.
omega. So let's validate really quick that that is in fact the case. Let's see, where would we want to start with that one? Let's see where they start that derivation. The angular momentum is the sum of the individual angular momentums, which is what they did right here. Little L sub I is equal to the mass there times R sub I times omega, which is the velocity. What's their reasoning there? Well, that is in fact the case, and we'll come back and re-talk about angular momentum and give more intuition for it tomorrow. But that's the end of the new material.
Okay.
So that's giving you enough to get started on homework. Tomorrow we'll do more example problems, help cement some of these ideas, re-explain them a little bit better, and then we'll continue with new material. Good?